the precise definition of a limit. This is also called the epsilon delta definition, or the epsilon delta definition. Epsilon delta. Okay, there is a delta that is like this, and that is the uppercase delta, and this is the small case delta. Okay, I will explain it several times before we write it down. It is a little bit long because I'm trying to explain and tell you several times the same thing. It looks difficult and weird. It will be very easy when you finally understand it, but it will take a few minutes. So please bear with me. Here is a function. And by the way, I will only ask you to look at linear functions. No quadratic or cubic or infinite limits, nothing. Just the simplest possible function. There is nothing simpler than this. Linear functions only. Okay, here's a linear function. F of x. And this is a, of course this is x, and this is y, and this is L. You may see other functions in WebAssign, or we're going to look at other functions, but the full proof only for linear functions, okay? But we may have other situations, but that's not the full proof. Okay. Looking at this graph, can you say whether I'm correct? That limit as x approaches a from either side of f of x is L. Would you say this is correct? That I'm correct when I write this based on my graph?
Yes.
Yes, of course. So what really happens here? Details of the procedure. I'm copying it here because I just want to move this page away. That's all. You don't have to copy it again. Okay. So what really happens is, if I choose an interval, symmetric interval. When we talk about a symmetric interval, we say this is a symmetric interval between -3 and 3, for example. Symmetric interval. So if I know that this is L, you can think of L in terms of a number. Right? L is a number, the limit exists. So let's say 10. It doesn't matter, I'm not going to put the numbers unless we need to. So if I want to choose a small, tiny interval around L, this upper limit of the interval is L plus a little bit. Can anyone give us, if the interval is symmetric, can anyone give us the lower limit of the interval?
L minus a little bit.
Obviously, sure. So if I choose epsilon positive, a small number, not 5, not 10, like 0.1 or 0.01 or 0.2. If I choose that, look what happens. This point, if I draw a horizontal line till the function and then down vertical, and if I do the same thing to this, and down vertical from the point it touches or crosses the function, then this epsilon will create an interval around A. Any epsilon I choose, right? I can choose this epsilon here, and I will get this interval around A. I can choose a smaller one, I can just choose a bigger one, but for every epsilon, if I choose epsilon, small, and I'll put in parentheses, for any epsilon, positive, I will be able to, so if I choose epsilon positive, I will find that epsilon will create, if you want, I will find an interval, not just an interval, I'm going to write the interval yet, so far, interval around A. Now, see, based on the graph of the function, I have two options. I have this length, which based on my graph is smaller than this length. I hope it's clear, right? So that's how my graph is. It could be different if I change the slope of the function. So the question is, which of these two lengths would I use? Because I also need to determine a symmetric interval near A, around A. So a symmetric interval around L will create an interval around A, but now I have to make a decision. Do I choose this width or this width? And the answer is I always have to choose the smallest of the two. Choose delta, the smallest distance from A. So obviously the smallest distance is this, so I'm going to consider this A minus delta and this A plus delta. So let's stop and see what we just did. By choosing an epsilon small, I constructed a symmetric interval around L. And when I wanted to see what happens around simultaneously, when I choose the epsilon, what happens around A, I realized that I get a small delta and a big delta. I always have to choose the smallest of the two. Okay. What happens now is such that if I choose or pick X close to A, can X be A?
No.
No, specifically no. Such that if I choose or pick X close to A, f of this X, whatever X is, f of the X will fall near L. How come? Here it is. If I choose X here, look what happens. This is f of X. If I choose X here, I will get close to L. Not outside of epsilon. That's the trick. But look what happens if I choose the wider delta. If I choose the wider delta, which is this, then I could possibly get an X here, which will not fall inside of the interval with epsilon. That's why we always have to choose delta as being the smallest. Okay, so now you're saying, what's all this? What are you trying to say with this? Here's what I'm trying to say. The limit of f of x as x approaches a is L. And now that double equivalency symbol, meaning this implies this, this implies this. I'm going to write it in words first, and then I'll show you those symbols so we can condense it. If you don't want to use the symbols, you don't have to. So the limit of f of x as x approaches a is L. This implies for any epsilon positive, I will find, or there exists, better, a corresponding delta positive. So let's stop for a moment. For every epsilon, I'll find a corresponding delta. Delta depends on epsilon. If epsilon is this, delta will be this. If epsilon is this, then delta will be something else. So every delta depends on epsilon. So limit is L. It implies that for any epsilon positive, I will find, or there exists, a corresponding delta positive such that when I pick x close to delta, and here, I'm sorry, close to a. And now I wanted to write in parentheses, the distance between x and a is less than delta. And I wrote delta by mistake, sorry. So such that when I pick x close to a, distance between x and a is smaller than delta. And I'll show you how we write that. So such that when I pick x close to a, f of x, f of this x will fall close to L. In other words, distance between f of x and L is smaller than epsilon. Guaranteed. And that happens only because the limit exists. Smaller than epsilon. Okay, so now I want to show, this is way too long. I highly recommend condensing it with symbols. But before we do that, I want to talk about this. And then talk about this. When we say that the distance between x and a is less than delta, we write it like this. This means the distance between x and a is smaller than delta. And I will also put here greater than 0. And you can say, but this is redundant. We know that the absolute value is positive. Yes, but this says that x cannot be a because it cannot be 0. And the other one, the distance between f of x and L is less than epsilon. We don't write it like this, we write it like this. F of x minus L less than epsilon. Okay, so now with symbols. Let me refresh your memory. This means for any or all. This symbol, we have not talked about it yet. There exists. This we haven't talked about yet, such that. These are mathematical symbols widely used. And now this definition will be on one, or will fit on one line, like this. So here is the epsilon delta definition of the limit, or the precise definition, same thing. In one line. Limit, maybe two because I write big. Limit as x approaches a from f of x is L, is equivalent to, for every epsilon positive, there exists a delta positive such that, as I said, I don't have enough room because I write too big, 0 less than x minus a less than delta will imply f of x minus L less than epsilon. Instead of half a page. For every epsilon positive, I will find, or there exists a delta positive such that when I pick x close to a so that the distance is less than delta, it's guaranteed that the function value of this number will be the distance between the function value and the limit will be less than epsilon. And this happens only because the limit exists. Let me give you just a quick counter example.